Hello, today we are going to talk to you about one of the basic properties of mechanical motion, which is called relativity of mechanical motion. What is it? When you and I consider the motion of any bodies, we must necessarily talk about what this or that body is moving relative to, because when we say that the speed of a car is equal to 10 meters per second, it is not quite clear what specific speed we are talking about. It is clear that by default we usually consider this velocity relative to the ground. But we should realize that we can take absolutely any body that is near this car as a reference frame, including this body can also move. And then the question arises, and how to determine the speed of this car relative to other objects that are near it? Hear about it just about us, and help us in the laws of relativity of mechanical motion, which we will consider today with you. In order to understand how this phenomenon works, we must study with you the law of addition of velocities, which was once introduced by Galileo Galilei, and which is the basis for solving problems on this topic. Let's look at it on an example. Suppose we have an automobile that is traveling at some velocity, v1, in a given direction on a road. When we talk about a specific velocity, it is important to acknowledge that the basis for measurement is the ground on which the object is moving. Thus, in our discussion, the person observing the particular vehicle will be regarded as the reference point for measurement. The velocity of a person relative to the ground is zero, that is, we consider him to be a stationary body. But what will the passenger in the second car, which is traveling in the same direction at the same speed, v2? In this case, the question then arises as to what happens if we move to another frame of reference that is itself moving. Just here we are helped to solve such a problem by the law of addition of velocities, which Galileo once told us about. Here we must consider directly several systems of account, a stationary one, a moving one, and the body itself, which we are going to study, and each of these objects has its velocities. If we look at the situation here, we can show that there is the speed of the car relative to the ground. In this case, it is a relative speed, that is the speed relative to this system of report. Then there is the velocity of the moving body itself, which we want to take as the reporting system. This is already a portable speed. That is, we will then transfer it to other objects that will be considered moving. And then there will be the absolute velocity of this car relative to the selected report system, in this case, this car. Let us consider an example of such motion based on the motion of this car relative to the ground. Now you and I can see that there is a car that is moving at speed v1 and speed v2. In this case, it's from the side of the observer who is directly on the ground. And our task is to look at the motion of the car. Let's label it number 1. Relative to car number 2. So, our task now, having applied the law of addition of velocities, is to consider how this will be applied to the example of the motion of these bodies. So, the law of addition itself is as follows. The absolute velocity, so we're going to denote it as VA, will be determined by the velocity relative, and the velocity of this object, we'll just call it v. If we talk about the vector sum, here we must realize that depending on the task, on how the velocity vector will be located, we must use the rule of addition of velocities in order to determine the sum of these velocities. And now our task is to go to the reporting system associated with the second car, and to do that, we're going to do a second figure, where the second car is now stationary. We move the observer to the second car. Let's draw him like this. And now our task is to consider what happened to the speed of this car. That is, if we stop this car and propose to consider it as a report system, it means that its velocity at this moment of time is 0. But what has happened to it? If we look from the point of view of an observer who is in this car, what will he see? He will see that around him all the objects that he observes through the window are moving towards this observer with the same speed. So it turns out that we transfer it to the ground and to the surrounding objects, and so we're transferring this v2 in this way. With turning backwards, we're transferring it to the surrounding objects. The car itself doesn't have this speed now. And the car that we were interested in, number 1, is still moving forward at a speed of v1. Then it turns out that absolutely the velocity of this car relative to our report system will be determined by the sum of two velocities: the speed of the car itself plus the speed of the reporting system in which it is located. What is happening here? In fact, relativity of motion occurs, and we consider it from the point of view of the change of the report system. That is the transition of a body from one report system to another. So if this pencil is the reporting system and the car is approaching it, then we see the movement on one side. But if we look at it from the point of view of the person who is sitting in that car, then he will see the pencil approaching him. So in this case, we just have to imagine what an observer inside some moving object will see. Thus, it turns out that the total velocity of a given body, or as we said, the absolute velocity, we will define as the vector sum of the two given velocities, Vy and V2. Now, when we speak already about the scalar sum of these quantities, that is, when we translate these equations into numerical values, then, taking into account the direction of these velocities, we see that they are directed in different directions. And so, in this case, we're subtracting the values of these vectors. Depending on which of these speeds is greater, two variants of events will occur. Either the first car will catch up with the second car if its speed is greater, or the second car will overtake the first car. In the reverse case, we see that this difference will be negative. So in this case, when we talk about the law of addition of velocities, we must remember that there is the velocity of the object, there is the velocity of the reporting system, and there is the velocity of the object relative to some fixed reporting system. Further, everything will depend on how these velocities are directed in relation to these systems. When these vectors are on one straight line, here we get quite simple solutions of problems, because we don't need to consider some complicated constructions with the help of triangle or parallelogram rules, as we did earlier. But let's consider now an example when we can consider this law of addition of velocities from a more complicated point of view. Suppose we have a train car that's moving forward at v1 speed. And suppose we have a ladder on the side of this train, is being climbed by a person at a velocity of v2, relative to this carriage. That is, he has his own velocity within the given reporting system. And the question arises, with what in the end the velocity with which the given person moves relative to the ground? That is, to find his absolute velocity relative to the stationary system of the report, which we take as the ground. In order to find this velocity, we again use the law of addition of velocities, i.e. we define the absolute velocity as the vector sum of the two velocities. The velocity of the report system itself, in this case it is a rail car, and the velocity of the person who moves inside this mobile report system. Then our task is to draw the sum of these vectors, i.e. to construct them, and we can do this by moving these vectors to one point, i.e. by combining their origin. Thus we will have the velocity v2 and respectively v. 1. According to the rule of vector addition, we can complete this figure to a parallelogram and draw its diagonal. This diagonal is exactly what will be the absolute velocity of this body. we can find this velocity easily enough by looking at what figure we have got. That is, when we talk about construction, about the graphical representation of the sum of vectors, naturally you get some figure. That is, it can be a triangle or it can be a polygon if there were several such velocities. But further, the problem comes down to finding the desired length of this vector, which we got as a result. Here, taking into account that the movements were mutually perpendicular, we have a rectangle, and in order to find the diagonal of this rectangle, we can use the Pythagorean theorem. Thus, it turns out that the velocity of a given person relative to the Earth will be determined already from the Pythagorean theorem as the sum of squares of velocities under the square root. Despite the increasing complexity, the underlying principle remains the same: the addition of velocities according to the basic law. Although the vector form remains constant, several variations arise when transitioning to the scalar form. And in practice, we will additionally see how this law is applied and practice on various tasks. This is the end of our lesson. See you all soon. Goodbye.